Right, is it record? Oh. Yeah, we're recording now. All right, cool. So we're moving on to section 8.3 today. This is relative rates of growth. So it's actually pretty complicated. You're going to have some technical terms like grows faster than, grows slower than, and grows at the same rate. So again, tricky words there. Those are technical terms. This would have been your do now if we were in-person learning. Of course we are not, so maybe use it as a warm-up. I know that some of these limits over here are difficult to read. All of the approach value is x approaching infinity. Except for number 3. X approaches negative infinity there. So maybe pause the screen and then come back. And we're back together. I thought I had the answers over here, but apparently they're here. There we go. So we should have 0, infinity, infinity, 0, and the end behavior model. Remember, that's just where we take the largest contributing term from each function, and that's our end behavior model. So 5 behaving like negative 3x to the 4th, you should be able to see that now. And for number 6, behaving like 2x squared, where we take that 2x cubed and the x and divide them to find our end behavior model. All right, so let's get into the technical ways. Oh, we don't need to do that because we're not doing homework quizzes. All right, so let's get into what I mean by faster and slower. So we will be talking about functions growing, quote, faster and, quote, slower than each other in this section. What does it mean for a function to grow fast? What family of functions do we have that grows like really fast? Hint, this type of function actually lends its name to an expression meaning grows really fast. Need another hint? Think Euler's number. So all of this sarcasm right here really would have lent itself to the in-person instruction a little bit better, but I guess we deal with what we have, right? So here I'm really trying to reference something blowing up exponentially or gets exponentially larger. We're trying to say that our gold standard for a fast rate of growth is an exponential function. And really, what we're going to use is e to the x. Obviously, faster and slower are subjective terms, and math doesn't really feel right when we're talking subjectivity. So we just come up with this as our standard fast growing function. It grows really fast. Anything that grows faster than it, we say grows super fast. Anything that grows slower than it, we say it doesn't grow quite as fast as exponential, but it still could be fast if it's faster than the slowest growing, or what we call a slow growing function. So y equals e to the x grows really fast. So that function grows really fast. Doesn't that mean that its inverse grows the opposite of really fast, meaning really slowly? Ah, okay, cool. So we can get our gold standard for our slow function. So again, whoa, that is not how we spell ln. What is wrong with me? Ugh. Full disclosure, right now, this is the end of the parent-teacher conferences, so I'm doing math at 6 o'clock at night. I'm not used to that. So just to wrap this up, fast is y equals e to the x. Slow is y equals ln of x. So let's go down here just to show you what I mean by grows really fast. Imagine that this right here is a chalkboard, right? Oh, here, I got an idea for making it into a chalkboard. Hey, look, it's on a chalkboard now. So you can't really see, oh, that kind of stinks because you can't really see the curve right here. But that curve is right at the beginning of this chalkboard right here. If I was to measure my chalkboard in terms of inches and scale this out in terms of inches, at about 3 inches on the x-axis, this function would already be up at 20 inches, which is pretty much bigger than it. At 10 inches, I would have to grow my chalkboard up 1/3 of a mile to be able to reach the height there. At 44 inches, the function would already have gotten to the height of, 2 million light years. And at 64 inches, meaning 5 feet, 4 inches on the x-axis, we would have to go to the end of the known universe to be able to graph this in the upward direction. All right? So that's what we mean by fast. It gets real big real quick. Now the opposite we have here is the inverse function, y equals ln of x. It goes exact opposite way. If we went out about 20 inches, that would mean we were only up about 3 inches. In order to reach a height of 1 foot, so to reach 12 inches, we would have to go to the right 2.6 miles. So I would probably be in Lake Erie at that point. To reach the height of 5 feet 4 inches, we would have to walk to the end of the known universe in order to get that height. So just think about that. Think of somebody you know that is 5 feet 4 inches. My mother, for example, is 5 foot 4 inches. In order for this graph to be able to go higher than she is tall, I would have to stretch out that way to the end of the known universe, which is just insane. So it grows really slow, is what I'm trying to say here. Now we have to talk about grows faster than or slower than. So you need a function to compare your function to. Again, generally, we're going to use y equals e to the x to say if it grows faster, or y equals ln of x to see if it grows slower. What you want to do, you want to look at the ratio of the size of the function at its end. So when you're trying to find out if a function grows faster than g of x or grows slower than g of x, either way, you're going to take the limit as x approaches infinity of the ratio of f of x to g of x. Or even if you're trying to find out if they grow at the same rate. All of the problems today, you're going to start off with the limit as x approaches infinity of a function compared to another function. If you get infinity out of that ratio, that means that the top grows faster. And consequently, the bottom grows slower. If you get 0, the top grows slower. And consequently, the bottom grows faster. If you get any number that is finite and is not equal to 0, the two functions grow at the same rate. And sometimes that grows at the same rate thing is kind of weird. Like this problem right here. There is a giant warning there. Please suspend your common sense. Which function grows faster? Y equals x or y equals 2x. So looking at this, we obviously can tell that both of these are linear functions, and the second linear function does have a bigger slope, so we might think that it grows faster. But we would be wrong. The way that we have to do this in terms of calculus, we take the limit as x approaches infinity, and you just put one of them on top. It doesn't matter which one goes on top. Eeny, meeny, miny, mo. This one, we're going to put 2x on the top, okay? So we have 2x divided by x. Now we evaluate that limit. We can tell that this limit does satisfy L'Hopital's rule. We have infinity over infinity, but it'd be so much easier just to rewrite this as the limit as x approaches infinity of 2, and then recognize that the limit as x approaches anything of 2 is just 2. It doesn't matter what x is going to be. That limit is just a constant right there. So here we have the limit of the ratio equals a number. That number is not 0. Therefore, y equals x and y equals 2x grow at the same rate, which again just kind of seems weird to us, again, because we're talking about slope. Now back to the whole which one goes on top thing. I am going to point out, again, it doesn't matter which one goes on top, which one goes on bottom, because we have limit as x approaches infinity of x over 2x is equal to the limit as x approaches infinity of 1/2, which is just 1/2. And we get a number that's not 0. Again, for the same rate, we just want a number that is not 0. Looking back at the setup over here, if we had chosen the fast one on the top, then we get infinity. If we choose the fast one to go on the bottom, we get 0. So really you have to interpret your answer to determine which one's faster, which one's slower. So again, it doesn't matter which function you put in the numerator. Now again, down here, grows faster is not the same as has a steeper slope. And the way that the book puts it actually kind of makes sense if you read this like 85 times, the book says that f grows faster than g means that for large x values, g is negligible compared to f. So we're trying to say if f grows faster than g, that means that f is infinitely bigger than it. Not 2 times bigger than it like we're talking about over here. We have to say it's infinitely bigger. Same rate, frowny face. Yeah, cool. So show that the function e to the x grows faster than x cubed as x approaches infinity. Again, doesn't matter which function you put on top, we just know that we have to have the limit as x approaches infinity. Every single problem starts off with that today and starts off with a fraction bar. Now, on that fraction bar, we're going to put one function on top and one function on the bottom. Already, we see what the answer is going to be. It says, show that the function e to the x grows faster than x cubed. That means that e to the x grows faster than x cubed. What we want to show is if we put e to the x on the bottom and x cubed on the top, we should get infinity. If we put the slower one, again, since e to the x is the faster, x cubed is slower. If we put x cubed on the top, we would get 0 off of this. I just feel like putting it this way. All right, so we've got the limit as x approaches infinity, e to the x over x cubed. So looking at that, I see that we have infinity over infinity from the last section. I know that I have to acknowledge that this is in the indeterminate form, and then I have to acknowledge that I am going to use L'Hopital. Limit x approaches infinity of derivative of e to the x is e to the x. Derivative of x cubed is 3x squared. Okay. We know that this is still infinity over infinity. We know that we're going to have to do this again. So we're going to have limit as x approaches infinity of e to the x over 6x. Okay, still infinity over infinity. We L'Hopital again, and we have limit as x approaches infinity of e to the x over 6. Finally, we're out of indeterminate forms. We've got infinity over 6. Okay. Infinity divided by finite is infinity. So therefore, we have e to the x grows faster than x cubed. Now here we do want to acknowledge that since we are answering a question, you don't want to be a jerk. Try to answer your question in the form of a sentence. And since it does say show that the function e to the x grows faster than x cubed, you would not want to put down x cubed grows slower than e to the x, although that does imply the answer to the question. Now something that I do want to point out here is sometimes you're going to be dealing with polynomials that are going to be bigger degrees than 3. Notice here we had to do L'Hopital's rule 3 times in order to get this down into non-indeterminate form. It's actually pretty formulaic when you have a polynomial, how we differentiate down to a constant. Like if I had x to the nth, and I wanted to differentiate that. So let's say y is equal to x to the nth. That would mean y prime is equal to n x to the n minus 1. Y double prime is going to equal n times n minus 1 to the n minus 2, which is x to the n. You can definitely tell that it's now 6:12 in the evening. I'm losing my mind here. X to the n minus 2. And we would have to keep doing this until whatever derivative we're on would be like the n minus 1th derivative here would be equal to n times n minus 1, brought down that n minus 2, all the way up until we had n, actually not n, all the way up until we had just 1. And then it would be x to the 0th power over here. So we actually have a way of writing out n times n minus 1 times n minus 2 times n minus 3. In this case up here, it would have been like the 3 times 2 times 1 here. We call that a factorial. So if you have an nth degree polynomial, I'm all right with you just using that n factorial. So just to show you what this work would look like if I want to summarize it the way that I'm saying down here, I'm all right with you saying limit as x approaches infinity of e to the x over x to the third is equal to infinity over infinity. So therefore, L'Hopital, a whole bunch of times, dot, 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 is equal to limit as x approaches infinity of e to the x over 3 factorial, which is equal to infinity. Because any factorial, it might be large, but it's still going to be finite right there. I will also point out that this only works because the other function is e to the x, which repeatedly differentiates to itself. All right. Yeah, whatever, we just did that. So show that e to the x grows slower than e to the cosine of x as x approaches infinity. Okay, so we're going to look at that, and we're going to say we want e to the x grows than. Oh wait, it doesn't even say whether it's slower or faster. Okay, so I guess we're going to have to figure out which one it grows, whether it's slower or faster. So we've got the limit as x approaches infinity of eeny, meeny, miny, mo, this one. We'll put e to the cosine of x up top and e to the x on the bottom. Now here we have e to the cosine of x over e to the x. We want to figure out which one does it grow, faster or slower. I have no frickin' clue. But what I do know is cosine of x is somewhere between -1 and 1, right? It oscillates between the value of -1 and 1. So what we have here is this is going to be the limit as x approaches infinity of e to some number, and that number is going to be between -1 and 1, divided by e to the x. So e to the n, again, is going to be some finite number because I'm doing e to some finite number. So this becomes just some number divided by infinity. Oh, well, that becomes 0. Therefore, e to the x grows blank than e to the cosine of x. And to figure out which one it grows than, faster or slower, look and see that e to the x is in the denominator. Since we get 0 off of this, that means the denominator grows faster. Here's the technical way that you would have to do it. Notice that I did flip it upside downsicles. So looking at that, technically we're talking sandwich theorem here, but really sandwich theorem just acknowledges that you have some sort of finite number, and some sort of finite number divided by infinity gives you that 0. So a couple more problems show that ln of x grows slower than x. Again, limit x approaches infinity of one function over another function. Again, we know that ln of x grows to infinity, so we do have infinity over infinity here, which we now know that we can use L'Hopital's rule to evaluate that. So we're going to have limit as x approaches infinity of 1 over x divided by 1, which last time I checked, 1 divided by infinity is 0. 0 divided by 1 is still 0. Forgot what function I was comparing it to. Grows slower than x. So again, we got ln of x growing slower than x on that one. I will point out that all of these questions for this section, the answers are pretty much just yes, because you're confirming what is told to you. Show that x grows at the same rate as x plus sine of x as x approaches infinity. Now here, you do have two choices on what you could use either one as your numerator, either x or x plus sine of x. There is a better one to choose. When you have a monomial versus a binomial, it's always better to put the binomial on the top. So when you have two terms, that's always the better choice. So we're talking about limit as x approaches infinity. I'm going to put that x plus sine of x up topsicles over x. And the reason why I put the sum up top is because now, since I have the sum in the numerator of the fraction, I can split the fraction up into two different fractions. So I can make this the limit as x approaches infinity of x over x plus sine of x over x. Now looking at that, the first term is just 1. This becomes 1 plus the limit as x approaches infinity of sine x over x. Now looking at that sine x over x, again, I know that sine of x is some number. So this is going to become 1 plus limit as x approaches infinity of some number n over x. I plug in infinity as x, and it doesn't matter what the number is up top. It's somewhere between -1 and 1, but wherever it is in that range, I'm going to have 1 plus 0, which ends up just being 1. Therefore, x and x plus sine x grow at the same rate. I'm just saying English class, so I'm alright with you using some of those text-in symbols, the at symbol. We're cool like that. Alright, so comparing the growth of the following pairs of functions. Normally I would just say, okay, go ahead and do these, but really, you can pause, and then you can come back and see how to do them. So looking at this one, I'm not actually going to put the conclusions. I'm just going to say which one grows faster or slower out loud. I believe it's on the next page where it shows that. So I'm just going to show you my strategy for evaluating these. Again, that first one, I see two exponential functions. It doesn't matter which one you put on top, whether you put e to the x or 0.5 to the x. Again, if you put the fast one up top, you get infinity. If you put the slower one up top, you get 0. So I'm just going to, it came first, so I'm putting e to the x up top over 0.5 to the x. Now here, it's important to recognize what happens when you do 0.5 to a power. 0.5 to a power makes the number smaller and smaller and smaller. What we actually have here, we have infinity divided by 0. And infinity divided by 0 is infinity. Let's say that doesn't work in my head. The way that I like to tackle these problems, I like to use my properties from Algebra 2 instead of using L'Hopital's rule, because L'Hopital's rule is just going to put me into an infinite loop of taking these derivatives over and over and over again. So I look at this as the limit as x approaches infinity of e over 0.5 to the xth power. Rewrite it as 1 power. And I happen to know that if you take a number bigger than 1 and multiply it by itself, the number gets bigger. If you take a number that is smaller than 1 and multiply it by itself, you get smaller. And that repeats ad infinitum until you get that number to infinity. If that doesn't make sense to you, think of what like 2 squared is. That's 4. Think of what 0.5 squared is. That's 0.25. And if I kept re-multiplying, again, if the number is greater than 1, it's going to be infinity. If the number is less than 1, then the power is going to be 0. Now looking at this, I happen to know that divide by 0.5 is the same thing as multiply by 2. And E is 2.71. Remember, that's why we celebrate E Day on February 71st. So this number, 2 times 2.71, is definitely bigger than 1. I don't need to know exactly what it is. Since this is bigger than 1, this is infinity. And therefore, e to the x grows faster than 0.5 to the x. Again, I'm not going to put the conclusion down. I'm going to say the conclusion. Number 2, limit x approach infinity. Put the sum up top, x minus ln of x over ln of x. We put the sum up top so that we can split it up and make our life a little bit easier. Limit as x approaches infinity of x over ln x minus ln x over ln x. I'm going to try to show an excessive amount of work so that I can make sure that this is perfectly acceptable. So this is going to become limit x approaches infinity of the x over ln of x minus 1. Again, 1 is a constant, so it can unlimitize there. Looking at this, I see this as infinity over infinity. So I'm going to use that L'Hopital's rule. Maybe put a note in here just to satisfy myself that I am acknowledging an indeterminate form here. So here, I know that I'm going to have limit as x approaches infinity of 1 over x minus 1. 1 over 1 minus x is x. When I plug in x there, I get infinity. Infinity minus 1 gives me infinity. Therefore, since I had x minus ln of x in the numerator, x minus ln of x grows faster than ln of x, or ln of x grows slower than x minus ln of x. Looking down here, we're going to take the limit x approaches infinity. I don't know, which one do we want to put on top? It doesn't matter. Let's put e to the x on the top. I'm just making this assumption that e to the x, since it's the fast-growing function, I'm thinking that it grows faster than the other one. Looking at this, okay, I've got infinity over infinity. Oh boy, that's a polynomial, a 1,000-degree polynomial. I don't want to have to do L'Hopital's rule 1,000 times. I'm acknowledging that L'Hopital's rule is going to occur here. That's supposed to be an ellipsis. Dot, dot, dot is equal to limit as x approaches infinity. E to the x differentiates to itself those 1,000 times. The x to the 1,000th power differentiates to 1,000 excitedly, 1,000 factorial. We have infinite over 1,000 factorial. Don't even try to plug it into your calculator because it is way bigger than your calculator can handle. By the way, your calculator can only handle up to a googol. So 1,000 factorial is larger than a googol, but it doesn't matter if it's larger than a googol. It's still smaller than infinity, so this ends up being infinity. Therefore, e to the x does indeed grow faster than x to the 1,000th power. And last but not least, again, we want to put the sum up top and the single term down below. So we're going to have x to the cube plus 3 over x to the squared, which is going to be the limit as x approaches infinity. Sum up top, so this becomes x squared over x cubed plus 3 over x squared. We could do L'Hopital's rule on that first term, but why would we when we can recognize that we have sorry if you guys heard my text machine go off there. My father chose this time to send me a text message. He doesn't know that it's parent-teacher conferences, though. And then I'm still at work. So we have the limit as x approaches infinity. X squared divided by x gives me 1 over x plus, well, nothing to simplify over here. That's 3 over x squared. But I do know from that first thing that we went over, yesterday, we have 1 divided by infinity, 0, 3 divided by infinity, that's 0 plus 0, that means 0. Dang it. Never pay attention to your parents sending you text messages. Going way back here. Look at that. That first term, I put it as x cubed, or x squared over x cubed. Stop it. Pull it back up here. Look how dumb I was there. I made such a stupid mistake here. It was x cubed and x squared. Oof. 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 To make math correct, you gotta make sure that you keep it in line and don't do any magic here. So we'd have x cubed over x squared plus 3 over x squared, which is equal to the limit as x approaches infinity, which now x cubed divided by x squared, that's x, good, plus 3 over x squared, which ends up being infinity plus 0, which is still going to be infinity. Therefore, the cubic grows faster than the quadratic. X cubed plus 3 grows faster than x squared. And there you go. There's all my conclusions written up there. I wrote them in spontaneously. This one is, I call this like the transitive property of relative rates of growth. It's just saying if f grows at the same rate as g as x approaches infinity, and g grows at the same rate as h, then we can cut out that middleman and say f grows at the same rate as h as x approaches infinity. So this is very similar to the transitive property of like equality or transitive property of congruence. Remember, if a equals b and b equals c, then a equals c. It's the same thing. If f grows at the same rate as g and g grows at the same rate as h, then f grows at the same rate as h. Why on earth would you want to do that? Well, for something like this. Some sort of garbage where you have f of x is equal to the square root of x squared plus 4, and g of x is equal to 2 root x minus 1 squared. We want to show that they grow at the same rate. Now, if I wanted to do this like I did every other problem today, I would have to do the limit as x approaches infinity of put 1 in the top and put 1 in the bottom. But my head hurts just looking at that. I mean, I know it's infinity over infinity, so I know that I'm going to have to do L'Hopital's rule. But if I did L'Hopital's rule, that's going to really it's a super difficult derivative to use here. So instead, what I'm going to look at is, I'm going to look at what the end behavior model is for each of these functions and choose a similar function that is easier to deal with. I'm going to make it up and I'm going to call it h of x. Once I find h of x, that's going to be a simple thing to deal with. I'm going to compare f to h, g to h. Hopefully they both grow at the same rate as h, therefore f and g are going to grow at the same rate. So looking here, I happen to see that I'm taking a square and square rooting it. I'm ignoring the plus 4 because the plus 4 does nothing when I get up here. So the square root of x squared, that's just going to be a linear. Looking over here, I've got that 2 times square root of x and square. Again, I know that I'm not dealing with the minus 1 because that's insignificant as x goes to infinity. So looking at that, I've got a 2, but I've also got a square root squared, so I know I'm dealing with a linear there as well. I'm going to compare both of these to the simplest linear function that I know possible. So now, I know that I can do the limit as x approaches infinity of f over h. I'm just going to show that this ends up being a number that is not 0. Now we could do L'Hopital's rule on this one, but L'Hopital's rule is going to be a pain in the butt, and let's be honest, I want to avoid using it. So what I'm going to do, I'm going to try to get this x underneath that radical. And the way that I get it underneath the radical, I introduce a radical and I unintroduce a radical. So looking at that, I'm going to just square root and square x at the same time. Why did I do that? Because I can. It's true. X is equal to the square root of x squared because I'm dealing with positive numbers, because I'm approaching positive infinity. So I'm allowed to do that. Once I do that, another thing that I'm allowed to do, now that both the numerator and the denominator are underneath a radical, I can just write this using one radical so that I now have x squared plus 4 over x squared. And now that strategy that we've seen all video, I have my sum in the numerator, so I can split this up into x squared over x squared plus 4 over x squared. X squared over x squared ends up being 1. This ends up being the limit as x approaches infinity of the square root of 1 plus 4 over x squared. If I plug in infinity, this becomes 0. 1 plus 0 is 1. Square root of 1 is 1. Hey, look at that. That's a number. That number is not 0. That means f and h grow at the same rate. Now, as long as g grows at the same rate as h, f and g grow at the same rate as well. So looking here, again, g has a sum involved while h does not have a sum involved. So I'm going to rewrite this as 2 square root of x minus 1 squared over x. Again, I get that choice. I always want to put anything that's more complicated in the numerator. And by more complicated, I mean involves addition, subtraction. I'm going to use the same strategy that I just used in the previous problem in that first step, but I'm going to kind of, well, actually, it's going to be the exact same thing. I'm just going to write it backward. So instead of squaring and square rooting here, since I have the square outside, I'm going to rewrite the denominator as the square root of x squared. And since both the numerator and the denominator have the same power, this can become the limit as x approaches infinity of u just 1 squared. We got 2 root x minus 1 over square root of x squared. Now, since my sum is in the numerator, I can split it up. I have the limit as x approaches infinity of 2 root x over root x minus 1 over root x squared, which is going to be limit as x approaches infinity of 2 root x divided by root x is 2 minus 1 over root x squared. Plugging in infinity, this becomes 0. 2 minus 0 is 2 squared, gives me 4. Therefore, g grows at the same rate as h. Now, do note that these are different numbers. One's 1 and one's 4. It doesn't matter what number they are. As long as they're a number that is not 0, the functions grow at the same rate. So regardless that the ratio ends up being different numbers, we still say that they grow at the same rate. So therefore, f grows at same rate as h. G grows at same rate as h. So f grows at same rate as g, which is what I was trying to prove. So that sentence is kind of fuzzy there. I'm not really, again, I'm not an English teacher, so I don't know how to talk good, but whatever. What you want to really illustrate is that you're independently comparing f to h and g to h, and therefore using that they both compare the same, compare as the same to h, they compare as the same to each other. Okay, think forever. All right. So here's one where you're actually given those functions. I mean, we could go through this one if you guys really want to. Do you? Okay, cool. Cool. So we want to show that all three of these grow at the same rate. Really, all we have to do is show that two of them grow at the same rate as one of the other ones, and therefore they all grow at the same rate. So what I'm going to do, I'm going to compare F2 to F1 and F3 to F1. Why am I comparing them all to F1? Well, that's because F1's the simplest looking function. And honestly, I don't know how I'm going to go about this one because this looks very freaking scary. I do know that it's going to start out as limit as x approaches infinity, and I do know if I'm comparing F2 to F1, I want this bad boy being on the top. So I'm going to have x to the fourth plus 2x squared minus 1 over x plus 1 over x cubed. So that looks scary. Again, we all know that I hate nested fractions. I don't know if you guys hate nested fractions, but I sure as heck do. So looking here, I would change this into the limit as x approaches infinity. Instead of divide by x cubed, I'll change that to 1 over x cubed times x to the fourth plus 2x squared minus 1 over x plus 1. Sorry for reading that part so fast, but I was literally copying the numerator from over here. I'm going to distribute my x cubed into the parentheses at the same time distributing my 1. We know that 1 is, as my son would tell you, the multiplicative identity. So this would be x fourth plus 2x squared minus 1 over x to the fourth plus x cubed. Okay, now we recognize that we're going to have to do some L'Hopital-ing here. We're going to have infinity over infinity. So using L'Hopital, we're going to have limit x approach infinity. I hope I don't run out of space here. 4x cubed plus 4x over 4x cubed plus 2x squared. Dang it, if only that denominator had canceled out already, we could be done, but it didn't. We're going to keep L'Hopital-ing here. So we would have limit x approaches infinity of 12x squared plus 4 over 12x squared plus 4x. Rock it again. L'Hopital. We get lim x approach infinity of 24x over 24x plus 4. Almost there. Maybe one more time. We're L'Hopital-ing again. Limit x approaches infinity, 24 over 24, which is equal to 1. All right, cool. Side note, if I had chosen the other way around, if I had put the funky looking one down in the denominator, that would have made this fraction the reciprocal, would have made this fraction the reciprocal, would have made this fraction the reciprocal. I could have ended over here had I done the reciprocal of that, but whatever. Sometimes you don't think before you do things. Then we'll have limit as x approaches infinity of comparing the other one, 2x to the fifth minus 1 over x squared plus 1 divided by x cubed, 2x fifth minus 1 over x squared plus 1 divided by x cubed, which is equal to, using the same strategy that I had before, limit x approaches infinity of 1 over x cubed times 2x fifth minus 1 over x squared plus x cubed. No. I didn't distribute my x cubed yet. Sorry about that. Plus 1. Distributing my x cubed into the denominator. Crap, I think I chose bad again. I think if I had put it in the other, the flipsidoodle, this would have been easier, but whatever, it's still accomplishable. Over x to the fifth plus x cubed which L'Hopital (10x fourth over 5x fourth plus 3x squared. It looks like I'm going to have to do this 3 more times here. L'Hopital lim x approaches infinity of 40x cubed over 20x cubed plus 6x. L'Hopital lim x approaches infinity of 120x squared over 60x squared plus 6. Okay, one more time. 240x divided by 120x. Finally, this other term goes away, and we're left with just 2. Therefore, F1, F2, and F3 all grow at the same rate. Whew. End of story. I believe I have that. Yeah, look at that, down here. I spontaneously wrote it all in red. That last problem right up there is the problem from the Mean Girls movie, which one of the nice things about the Mean Girls movie is not the, well, actually the writing's pretty good, because a lady named Tina Fey wrote it. And Tina Fey did what is called dramaturgical work, and she made sure that the problem at the end of that movie, where Caddy says the limit does not exist, actually worked out. This is the math for that problem. If you want to see that problem actually worked out, come see me someday during office hours. Whatever. All right. See you guys tomorrow.